Hi, in this video I'm going to be going through some hopefully helpful advice and comments about how to do homework number 5 on the complex regressors topic. The first problem involves some data from the twins data set, and we're going to try to explain a response variable with 3 levels of socioeconomic status or social class. Level 1 is high social status, level 2 is medium middle class social status, and level 3 is lower social status. The data set comes from IQ scores from identical twins. One of the members of the twin pair was raised in a foster home, and the other member of the twin pair was raised by the birth parents. And the variable that we're going to analyze in problem 1 is the difference, IQD, between the biological raised twin and the foster raised twin. The IQ of biological minus the IQ of the foster raised twin. And what we're trying to do is determine if there's any evidence to suggest that these IQ differences change depending on the social class of the biological family. And so we're going to do this main effects model where the average IQ difference is a function of beta naught plus beta 2 U2 plus beta 3 U3, where U2 is an indicator variable that takes on the value of 1 if the biological parents were in middle class and 0 otherwise, and U3 is an indicator variable that takes on the value of 1 if the biological parents were in lower social class and 0 otherwise. In the data code block here, you can see that I'm declaring the variable C as a factor and giving them labels high, medium, and low, and then make the difference variable IQD, biological IQ minus the foster twins IQ, and then we do box plots. So let's just take a look at these box plots for a minute and see if we can understand what we're looking at here. The first box plot is for children born to parents who are in higher social status. A 0 would mean that the child raised by the biological parents had the same IQ as the foster raised twin. You'll notice that for the high class social status parents, the box plot is shifted to mostly positive values for this IQ difference. What do positive values mean? The only way you can get positive values is if the IQ for the home-raised biological member of the twin pair would be higher than the IQ for the foster-raised sibling. And so in this case, children that are raised by the biological parents seem to have an IQ advantage over their foster twin. For middle class or medium social class families, you'll notice the box plot is almost evenly centered around 0. There's no particular difference between the biologically raised twin and their foster raised sibling. For lower social status, you'll notice that a lot of these differences are negative values, and that would mean that getting out of the lower social status home and being in the foster family is increasing the foster IQ relative to the biological family's IQ. And that's the general pattern that we see. The question will be, are these statistically clear differences or not? Our model is estimated here with mod, linear model. IQ difference is a function of the social class of the biological parents. We get the model output right here like this. We have an intercept of 4.29. We have an adjustment for medium of negative 2.62 and an adjustment for low of negative 6.79. Make sure you review the notes to understand these coefficients, because the intercept is going to be interpreted by plugging into the model the u variables u2 and u3 both being equal to 0. So if medium class and lower class are both zeros, the response is the intercept beta naught, and that would be for the high social status. And so that's how to interpret the intercept. Make sure you remember how to interpret the coefficient for medium. This is going to be found by plugging in U2 equals a 1 for a medium social status family. U3 will be a 0, and so the summation of the intercept coefficient and the beta 2 hat coefficient will give the estimated value for medium social status. So the 4.29 plus the negative 2.62 gives you the estimated IQ difference for medium social status. In other words, this is the difference between medium minus high social status. And this difference is the difference between the average IQ difference for low social status minus high social status. And so these are differences of medium minus high and low minus high IQ differences. The confidence intervals for these parameters are given right here with confint, and then we use an LS means function for our estimated model to get estimated averages for each of the groupings. And so you can see that the estimated IQ difference for high social status is given here. It's a positive number. The estimated IQ difference for medium, the estimated average is a slightly positive number, and the estimated average IQ difference for lower social status families is a negative number. And then the remaining part of this output is estimated differences for all groups minus others, estimated differences, and p-values for those differences. I wouldn't look at these p-values. They have a special Tukey adjustment which we haven't talked about. Here is an effects plot that shows those averages declining as you go down in social status, a declining advantage for the biological raised twin. And now we get to our first question. Compare high social status to medium social status with a confidence interval. Give a confidence interval and make a conclusion based on this for 2 points. You got to remember, in our model and in our model output, what controls the difference between high and medium social status? And I'll remind you that back in our model output, this coefficient is controlling the comparison between medium and high. The problem and the thing to be careful with is this number that's given right here is for medium minus high. And I'm asking you in the homework problem for high minus medium. And so please make sure that when you use the confidence interval output, that you carefully make sure that you have the confidence interval boundaries for high minus medium and not medium minus high. What's being presented here is the boundaries for medium minus high, not high minus medium. So make sure that when you use your confidence interval in your answer that you use the appropriate one, and do not simply copy this one. By making a conclusion, you're going to want to be addressing whether there is a difference between these two groups that is different than 0. So please notice your confidence interval for that comparison and notice whether or not 0 is contained in the interval, and then make your argument based off of that fact, like we have done in other homeworks and the notes. Part B, compare high social class to low social class with a hypothesis test. Please be careful about p-values that are kind of small. I don't want you to just dismiss them as not significant. I think there is some evidence for smallish p-values in this range, so please don't dismiss them. They provide some evidence to doubt the null hypothesis. I want you to carefully state that. Remember that the comparison between high and low social class is given in this output. It's controlled by this coefficient, and we have a test statistic and we have a p-value. Make sure you remember that this is comparing low to high, and I am asking you in the problem to compare high to low. So make sure you appropriately alter the test statistic and make sure you give an appropriate conclusion based on that. Finally, I want you to compare medium social class to low social class. And we're going to do that with this linear hypothesis test. And that gives a F statistic, which is given right here. And it gives a p-value right here. And I want you to use that test statistic and that p-value to make your conclusion about comparing medium social class IQ difference to the lower social class IQ difference. So please use this output for this test statistic and this p-value. Finally, what's the estimated IQ difference for high social class birth parents? Please consult either the LS means output for that estimated average, or perhaps you can get it from the model summary and report the value. Let me know if you have questions with that. In problem 2, we use the same data set, except we're going to use a slightly different model. We're going to use a model that has the IQ of the foster raised twin to be the response, and we're going to have the IQ for the biological raised twin to be the quantitative predictor, and then we will allow different model components for the social class. And the first model that we create here, the model that we're going to use in this problem, is the main effects model that has an adjustment for social class and a quantitative predictor IQ for the biological twin. If you scroll down, you'll see some scatter plots showing just in general that for twins where the IQ for the biologically raised twin is higher, the foster raised IQ is higher as well. And when the IQ for the biological twin is lower, their foster raised twin is also lower. And this demonstrates probably the genetic effect and similarity in IQ because these twins are going to be genetically alike. They just will have different environments. When we look at the second plot, you can see basically parallel lines placed on the points for each of the social classes. So the red line and dots are for the twin pairs born to high social class parents, the green for medium social class, and the blue for lower social class. And you can see that basically for low social class, the foster raised twin typically does relatively better relative to the biological raised twin if they're in the lower social class, because the foster raised twin is getting out of the low social class environment and having a better rearing environment than the twin that stayed behind at home. And that effect is reversed for high social class. The foster twin does not do as well for a given biological IQ. Staying in the home, or in this case the foster child getting out of the home, has a reduction. So if you think about an IQ for a biologically raised twin of 100 in a high social class home, the foster twin pair has about a 95 IQ, where the biologically raised twin has about 100. And so there's a penalty for getting out of the high class home. The foster child faces a penalty. Whereas in a low social class home, the biological twin of 100 getting out of that home gives the foster twin a 2 or 3 point advantage over the biologically raised twin. And the question is, what is the model and how do we interpret the model for this kind of structure? And so we have our estimated main effects model right here. We have adjustments to the intercepts of the different lines with the medium and the low coefficient adjustments. And we have a slope for the IQ quantitative predictor. And then we have confidence intervals for these parameters. Let's take a look at our questions. Oh, and here's the effects plot. You can see the benefit from getting out of the low social class environment on the social class variable, and you can see the strong upward pattern correlation between the two IQs. In part A of problem 2, it says interpret the beta not 2 parameter and make a statement about the significance using p-value. And the model that we're using right here is explaining the foster IQ with an overall intercept, an intercept adjustment for medium class, an intercept adjustment for low social class, and the slope and the relationship between the two IQs, which is common for all groups. You're being asked to interpret the adjustment for medium social class. And so what you should remember from the notes in this model is that this is the intercept adjustment going from high social class to medium social class. Basically the transition of going from red to green. And the estimated change for that is given right here in the output for the medium coefficient, and that change looks like about a 2 IQ point increase. It's going to be this value right here. The test statistic and the p-value are also given in this output for controlling that comparison, and I want you to use that p-value and that estimated value for the beta hat in the interpretation, and use the p-value to talk about what this beta parameter is controlling and what it means, and if it is statistically clear based on the evidence given by the p-value. The second part, part B, is to talk about the beta 1 parameter. That's the parameter that controls the connection between the biologic IQ and the foster IQ. It's this parameter right here, beta 1, and you need to do the interpretation of that value from the output. The model output is given right here again, and so use the estimated slope coefficient in the output to interpret the value, and then use the confidence interval for that coefficient to make a statement about the relationship, and is there a relationship between the biologic and foster IQs based on that parameter. Problem 3 is from the Berkeley Guidance Study for Children. In this one we're going to use all of the data, both boys and girls, and the model we're going to examine is a model that connects height at age 9 with adult height at age 18, and we'll have separate lines for the two sexes, the two genders, male and female. And so this is going to be a model that has separate straight lines. And if you want to visualize that, here are the separate straight lines for the orange-red points, the males, and the aqua-blue line for females. Separate lines and separate slopes and intercepts. It looks sort of parallel here, but we'll need to determine that with our model. And the model that we're going to estimate is an interaction model that has a separate sex intercept adjustment, a slope term for height at age 9, and a changing slope term based on sex by height 9 interaction. The beta 11 parameter controls the difference in slope for the two sexes. The beta 1 parameter is going to be the slope for the height by height relationship when sex is equal to 0, and I believe sex equal to 0 here is going to be for the males. So this is the slope coefficient for males. This is going to be the change from in slope going from males to females, and this is going to be the change in intercept going from males, the male intercept, to the combined one, which is male and female intercept. And here you get the estimated coefficients from that model and confidence intervals for those coefficients. Let's see what questions we have. Here's the effect plots. Effect between height and height for males, height and height for females. And we have our first task is to interpret the beta 0.1 parameter from our model. The second one is for interpreting the beta 1 parameter. And the third one is to interpret the beta 11 parameter. The beta 0.1 parameter is given right here in this model equation. It is controlling the difference in intercept going from males to females. So use the model output and interpret the change in intercept parameter and use the p-value in making your conclusion about the strength of evidence and what it says about the difference between males and females. The beta 1 parameter is the slope parameter for the males between the height at 9 and the height at 18, and I'm going to have you use a confidence interval to present your strength of evidence and your conclusion about the connection between those two variables. Beta 1.1 is measuring the change in slope, and so I want you to use the model output. Remember, beta 1.1 is going to be dealing with this line, and so use the p-value and the value in the output to interpret the value and to talk about the strength of evidence. In part D, we're going to have children that are 135 centimeters tall at age 9, and I want you to come up with an estimate for how different their age 18 heights are going to be between a boy and a girl that were both 135 centimeters tall at age 9. And you can do that with the ls-means command for your model, and we want to compare the sexes at a height 9 of 135. Here is the difference in height between males and females. This will be in inches, and this will control the significance of that comparison. I want you to be able to read this output and come up with the estimated difference between boys and girls. In part E, the same situation. Boy and girl are both 135 centimeters at age 9. Is there evidence that the heights differ between the boy and the girl? I want you to use the significance in the p-value to make your statement about is there evidence they're different and how are they different. Final problem is a problem that uses maximum salary explained by a job score variable. There's evidently a connection between job score and the salary that people make. And the question of interest in this problem is whether the salary has a difference depending on whether it's a female-dominated profession or not. And so we created an indicator variable called dom_m, which takes on a value of 1 if it's a female-dominated profession, and it takes on a value of 0 if it is not a female-dominated profession. I've given it a coding of M for male-dominated. It really isn't true, it's just not female-dominated. And F is the designation for a female-dominated profession class. And because we have curved relationships here in the data, we'll use a splines approach, and we'll have a separate adjustment and separate splines depending on whether it's female dominated or not. And I'm going to want you to use this model output to talk about how the functions are different depending on whether it's a female dominated profession or not. Right here is a variable that controls a comparison, and dom_m means for a male-dominated or at least a not female-dominated indicator. And so that's what this second M means here. And so this is going to measure the change in maximum salary. And so I want you to answer these questions. First of all, talk about why we would want to use splines and not a straight line. In part B, I want you to talk about how much difference there is for female-dominated versus non-female-dominated professions from our output. Give a value for how much dollar difference that is. And then I want you to interpret whether this difference is statistically significant and clear evidence for a difference between female-dominated and non-female-dominated professions using the model output. Let me know if you have questions about this homework.